Hello students, in this video lecture I am going to discuss the problem of finding shortest route between two given cities. Now suppose we are given a road map of cities, as in this case there is a road map that is given to us. Here in this diagram or in this road map there are points which have been labelled with alphabets A, B, C, D, E, F, G, H. Now these points are nothing but they represent cities. And then you can see there are lines joining these points or these cities. For example, there is a line which joins the city A with city B, or point A with point B. Now this lines which is the line AB, this simply represents the road joining city A and city B. Likewise, there is a line joining the point A, point B and point G. Which is nothing but this is again a road BG which joins city B with city G. So likewise the other lines joining the other vertices can be interpreted. Also we can see that there are numbers which are put along with each line. For example, along with the line AB or along with the road AB, there is number 7 that is written. Along with line BG, there is number 4 that is written. Now these numbers represent the distance between the corresponding cities in kilometers. For example, as I said that A and B, these are joined by a road AB, and 7 is written above AB. So this simply means that the road distance between city A and city B is 7 kilometers. Again, there is a line joining city B and city G, and 4 is written over BG. This simply means that the road distance between B and G is 4 kilometers. So likewise, the other numbers the other numbers which are placed over every edge, they can be interpreted. Now the problem that we have here in this case is that we have to find out the shortest route joining city A and city H, which means that we have to find out that sequence of edges joining city A and city H, the distance traveled along which is the shortest, or the distance traveled along which is the least. Now we can solve this whole problem by viewing it as a problem of graph theory. Now the question is, what is graph theory? In my earlier videos I have already explained what graph theory is all about, but for the sake of this video, let me just again give you an overview of what graph theory is all about. Now as far as graph theory is concerned, graph theory is a field of mathematics which deals with diagrams which are called graphs. And as far as a graph is concerned, a graph is a diagram which has two basic components. The two basic components of any graph in graph theory are vertices and edges. And if we take a look at how the graph looks, any graph would look somewhat like this. This is just one example that I am taking, but different graphs will look differently depending upon the number of vertices and the number of edges they have, and how the vertices are joined with edges. So accordingly graphs will have different shapes. So a graph somewhat looks like this, where these circles or these points are called vertices mathematically, and the lines joining these circles, these lines are called edges mathematically. So any graph in graph theory would look like this. Now as far as this roadmap is concerned, now this roadmap can be viewed as a graph in graph theory, where these cities that we have, the city A, the city B, the city C, the city D, all these cities which are points in this roadmap, they can be regarded as vertices. And then the lines joining these cities, for example the line joining city A and city B, or the point A and point B, these lines can be regarded as the corresponding edges. So this roadmap is very much a graph where the points represent the cities, and the lines joining those points represent the roads joining the corresponding cities. Now and as far as these numbers are concerned, which are put along with every line, these numbers can be regarded as weight of the corresponding edges. For example, we have that on the edge AB, the number which is written is 7. So this 7 can be regarded as the weight of edge AB, and this is the weight of edge AB, or WAB, where WAB refers to the weight of the edge AB. So likewise the other numbers can be interpreted. For example, this number 4 would refer to the weight of the edge BG. Then this number 2, this represents the weight of the edge df, and so on. So this particular roadmap, and therefore in that sense, can be regarded as a graph where the points are the cities, where the lines joining those points are the roads which join the corresponding cities, and the number or the distance between the cities is the distance between any two cities is the weight of the corresponding edge that we have joining those cities. So when you regard this roadmap as a graph in graph theory, then we can find out the shortest route joining the point A and the point H, or the vertex A and the vertex H, by using a algorithm which is called the shortest path algorithm. And the shortest path algorithm, namely, that we are going to use in this particular video for solving our problem is called the Dijkstra's algorithm. So this is an application of the Dijkstra's algorithm that I'll be describing in this video of finding the shortest route between two given cities A and H. So this is how the algorithm proceeds. So from now on, we'll be regarding this roadmap as a graph in graph theory, where the points or the corresponding cities would be regarded as vertices, and then the lines joining these points, or the roads joining the corresponding cities, they would be regarded as edges in the graph. And then the numbers which are put along with the lines, or the distances that are given along with the roads, these would be regarded as the weights of the corresponding edges, which means that if there is a point x and there is a point y that are joined by a line xy, so x and y will be actually regarded as vertices, and this line xy will be regarded as an edge. And if the number d is put along with the edge xy, then d would actually be regarded as the weight of the edge xy, and the notation that we use for the weight is weight of xy, or this weight can be even written as we, where e is nothing but this is the edge xy. So these are the notations that we will these are the things that we have to keep in mind when we regard this roadmap as a graph in graph theory. Now using the Dijkstra's algorithm, or the shortest path algorithm, the first step is to how to start the algorithm. Now in all the steps, what we'll be doing is that we'll be labeling each of the vertex which is given in this graph. Now there are the vertices that are given in this graph are A, B, C, D, E, F, G, and H. So what we'll be doing is that in this whole algorithm, we'll be giving labels to these vertices from A to H. And to start the algorithm, the first step is that the label that we will give to the starting vertex, A will be the starting vertex, and the label that we give to the starting vertex is -0. Now what is the meaning of this label -0? Now this dash simply refers to, now before I even come to the meaning of this label -0, you have to imagine that you are starting your journey from the city A or the vertex A, and you have to end your journey at the city H or the vertex H. And in finding and doing in the due process of doing this journey, you have to find out that route, or you have to find out that sequence of edges joining A to H, along which the distance traveled is the least, along which the total distance traveled is the least. Now if you have to find out the total distance that you have traveled in moving from A to H, this means that you have to add the distances which are associated with each edge which is in the sequence of edges. Now this is the sequence of edges that you have traveled, and there will be a distance, or there will be a weight that will be associated with each edge. So every edge will have a weight. So if you add all these weights which are associated with every edge, this edge will have a weight, this edge will have a weight, this edge will have a weight, adding all the weights of all the edges that are in this sequence, you will get the total distance or the total weight. And you are looking for that route joining the starting vertex A to the end vertex H, along which the total weight or the total distance, they are both the same, this should be minimum. So you have to in a way imagine as if you are doing a journey from A to H, and you have to find out that route from A to H along which the total distance traveled is the least, or the total weight is the minimum. Now we are starting our journey from the starting vertex A, and this dash, and we are giving label this to A, which is dash 0. Now here dash is interpreted as the vertex, the vertex that you have traveled last before you came to A. Now there is no vertex that you have traveled before you reached A, because A is the starting vertex. There is no vertex before A that you have traveled, so that is why I put a dash. And then 0 is the distance that you have traveled so far to reach till the vertex A. Now again, there is no distance that you have traveled to reach the vertex A, because you are starting your journey from A. So that is why this label dash 0 has been given. This dash means that there is no vertex that you have traveled so far to reach till the vertex A, and this 0 means that there is no distance that you have traveled so far to reach the vertex till A. So the first step to start the algorithm is that the starting vertex, which is A in this case, is given label dash 0. This is the first step. So I give the label dash 0 to the vertex A. So I'm putting label dash 0 along with A. So this is the first step. So every time I will go on updating the labels, and we will go on repeating the process till all the vertices have been labeled, including the last vertex H. So this is step 1. Now moving on to step 2. Now starting with step 2, now in this step we'll be taking an account of all the vertices that have been labeled so far. Now till now we have labeled only one vertex A, and the label that we have given to A is dash 0. So what we do is we find all the labeled vertices, and corresponding to each labeled vertex. So this is the first step, find all the labeled vertices, and then corresponding to each labeled vertex, we find the unlabeled, adjacent unlabeled vertices. So corresponding to each labeled vertex, find the corresponding adjacent unlabeled vertices. So now what does that mean? Now first of all, the only labeled vertex that we have so far is A, and the label that we have given to A is dash 0. Now corresponding to this labeled vertex A, we have to find out all the adjacent unlabeled vertices. Now if we take a look at A, now what are the adjacent vertices to A? Now those vertices will be adjacent to A which are connected to the vertex A by a common edge. So if we take a look at this graph, then the vertex B is behaving in such a manner that it is adjacent to A, because there is a common edge between A and B, joining A and B, which is the edge AB. Then again C is the vertex which is adjacent to A. Then again D is the vertex which is adjacent to A. So these are the three vertices that we have which are adjacent to A, because all the three vertices B, C, D have a common edge with the vertex A. There is a common edge joining the vertex A and these three vertices. AB is the common edge between A and B, AC is the common edge between A and C, and AD is the common edge between A and D. So now again we can see that these three vertices B, C and D are also unlabeled. No labels have been given so far to B, C and D. So B, C and D are three adjacent unlabeled vertices corresponding to the labeled vertex A. So there are three adjacent unlabeled vertices that you have, B, C and D, corresponding to the labeled vertex A. Now what we do for these three vertices is that we try to find out what labels we can give, if possible, to these three vertices B, C and D. Now as I said, that you have to imagine as if you are doing a journey from A, the starting vertex A, to the end vertex H. So from A there are three possibilities. You can either move from A, you can move to B, or from A you can move to C, or from A you can move to D. If from A you move to B, in that case the distance traveled in moving from A to B, the total distance reached till B would be, if you want to calculate D dash, if I'm denoting D dash as the total distance traveled in moving, that will be this distance 0 plus 7. 0 is the distance which we have traveled to reach till point A, plus the distance traveled in moving from A to B, which is the weight, which is 7, which is actually the weight of the edge AB. So D dash is going to be it's going to be 0 plus 7. So this means actually the 0 is actually dA, which is the distance that you have traveled till A, plus the weight of the edge AB, and this is 0 plus 7, which is 7. The same thing we do for vertex C. In case you choose from A, you choose to travel to C, then the D dash for C, which is the distance traveled to move till the vertex C, will be the distance you have traveled till the vertex A plus the weight of the edge AC, because you will be traveling along AC. So weight of the edge AC. So this is going to be 0 plus 6, and this is going to be 6. Again, the same thing we do for the vertex D. We calculate D dash. D dash is going to be equal to dA, the distance that you have traveled to reach till the vertex A, plus the weight of the edge AD, because you will be traveling along the edge AD to reach the vertex D, and this is going to be 0 plus 5, and this is going to be 5. So these 3 D dashes are found out. After you have found out these 3 D dashes, what we do is we find out the minimum of all D dashes that you have calculated, which means that we find out the minimum of 7, 6 and 5, and the minimum of 7, 6 and 5 is obviously 5, which occurs for the unlabeled vertex, unlabeled adjacent vertex D corresponding to the labeled vertex A. This means that this is the vertex which is of importance in this step. This is the vertex which will get a label, and the label that we'll be giving to D would be, the label would be A5. This is the label that we'll give to D, because A was the last vertex which we have traveled before we reached D, the vertex capital D, because the vertex capital D is reached after you move from A to D along the edge AD. So A was the last vertex that was traveled, and also because the adjacent unlabeled vertex D corresponds to this labeled vertex A, so we will write the labeled vertex A over here, and 5 is the distance that you have traveled in reaching till the vertex D. So this 5 stands for the D dash that we have calculated. So this is the 5 that we have written over here. So the label that the vertex capital D will have is A, 5, and in fact this particular label can be expressed as A, DD, where this DD, where this DD, this particular DD stands for the distance that we have traveled to reach till the vertex capital D. So this DD is actually equal to 5. So this is the vertex which is labeled in this particular step. So we, in the graph, we label this vertex capital D as A, 5. So by the end of step 2, there are 2 vertices that have been labeled so far. One is the vertex A, whose label was given as dash 0. This is the label that we have given to the vertex A, the starting vertex, and the vertex D, which has been labeled as A, 5. So this is the end of step 2. Now we would be starting with step 3. In step 3, we will be moving just parallel to what we did in step 2. That is, we would be finding every labeled vertex, and corresponding to each labeled vertex we'll find the corresponding adjacent unlabeled vertices, and then we'll be making calculations for D dashes for each of the adjacent unlabeled vertices, and then we'll find the minimum of all the D dashes the way we did in step 2. And after finding out the minimum at whichever unlabeled adjacent unlabeled vertex the minimum occurs, that unlabeled vertex, that adjacent unlabeled vertex would be the vertex that would be labeled at that particular step. So in every step we would be repeating the same procedure. So moving on to step 3 of the algorithm. Now let us take an account of all the vertices that have been labeled so far. Now there are 2 vertices that have been labeled so far: the vertex A, which has label dash 0, and the vertex D, which has label A5. Now for each of these 2 labeled vertices we find the corresponding adjacent unlabeled vertices. Now corresponding to A, the adjacent unlabeled vertices are B and C, which you can see in the graph. So there are two adjacent unlabeled vertices B and C. D is also there, which is adjacent to A, but D has already received a label, so we will not take the vertex D, which is adjacent to A, in consideration, because since it has already received a label. So B and C are the adjacent unlabeled vertices that we have adjacent to the labeled vertex A. Now corresponding to B, we find out D dash in a similar manner. D dash is DA plus weight of the edge AB, because we have to just imagine as if from the vertex A we are moving to the vertex B via the edge AB. So D dash is going to be the distance traveled till A, which is DA, plus the weight of the edge AB. So DA plus weight of the edge AB, which means that this is going to be equal to 0 plus 7, because the value of DA is 0. This is your DA. In the label you can see this is your DA, and 7 is the weight of the edge AB. So this is 0 plus 7, which is 7. And then again we will calculate D dash for C. When you are calculating D dash for C, again you will have to imagine as if from the vertex A you are moving to the vertex C. So D dash for C is going to be DA plus weight of the edge AC, which means that this is the distance traveled in moving till A, and the weight of the edge AC is the distance traveled in moving from A to C. So this is going to be 0 plus 6, which is going to be 6. So D dash for B is 7 and D dash for C is 6. And now accordingly the same thing we do for the labeled vertex D, whose label is A 5. This is the label that D has. And now we find all the vertices which are adjacent and unlabeled corresponding to the labeled vertex D. Now there are two vertices which are adjacent and unlabeled corresponding to the vertex D, and they are F and E. These are the two vertices. So F and E are the adjacent unlabeled vertices. Now corresponding to F, we calculate the D dash. So again, when you are calculating D dash for F, you have to imagine as if you are moving from D to F. So this is going to be D, the distance traveled till D, plus the weight of the edge DF. This is the weight of the edge DF. And DD is actually this 5 in the label. This is your DD. So this is going to be 5 plus the weight of the edge DF is 2, which is 7. So this 7 is the D dash for F. And the similar thing we do for the vertex capital E. We calculate the D dash for the vertex capital E, which is corresponding to the labeled vertex D. So this is going to be DD plus you have to imagine as if from D, the vertex capital D, you are moving till the vertex capital E via the edge DE. So this is going to be weight of the edge DE. So the total distance traveled is DD plus weight of the edge DE, which is going to be equal to 5 plus 4, which is going to be 9. So 9 is the D dash for the vertex capital E. So there are 4 D dashes that we have: 7, 6, 7 and 9. Now what we do is we calculate the minimum of all these D dashes, which means 7, 6, 7 and 9, and the minimum of course occurs at 6, which is corresponding to the unlabeled vertex C. This is the unlabeled vertex for which the minimum is occurring, and this unlabeled adjacent vertex corresponds to the labeled vertex A, which means that C is the vertex which is of importance in this step, and C will receive a label, and the label that C will receive will be A, 6, because A was the last vertex that you have traveled before you reached C, and then or A was the labeled vertex corresponding to the unlabeled adjacent vertex C. So you have to write the labeled vertex over here, and 6, this is the D dash for C. So in fact this 6, as I already told you, using the notation that we have been following, this 6 can be written as DC, which is the distance traveled in reaching till the vertex C. So A6 is the label that C receives. So I put the label A6 in the graph that we have is 6. So by the end of step 3, there are 3 vertices that have been labeled so far. One is the starting vertex A, which we gave the label -0. Then in step 2, we received we got a label for the vertex D, which is A, 5. And now by the end of step 3, the vertex C also has been labeled, and the label that the vertex C has received is A, 6. So this is the end of step 3. Now moving on to step 4, we proceed in a similar manner. We just find out all the labeled vertices, that is all the vertices that have received label so far. Now there are 3 vertices we can see from the graph which have received a label. One is vertex A, the other is vertex D, and the third one is vertex C. The label which A has received is -0. This is the label we gave to A in the beginning. Then the label which has been received by D is A5, and the label which has been received by C is A6. Now corresponding to each of these labeled vertices, we will find the adjacent unlabeled vertices that we have. Now corresponding to the labeled vertex A, there is only one adjacent unlabeled vertex, namely B, because B is adjacent to A, as well as it has not received a label so far. So B is the adjacent unlabeled vertex corresponding to the labeled vertex A. So corresponding to this adjacent unlabeled vertex, we calculate, which is B, we calculate D dash, which is the distance traveled in reaching till B. Again, you have to imagine, if you look at the graph, we have to imagine that from the vertex A to reach to vertex B, we will be following the edge AB. This is the route that we will be following. So D dash is going to be equal to dA, the distance traveled in reaching till A, plus the weight of the edge AB. And dA is this. This is dA. dA is 0. So this is going to be 0, plus the weight of the edge AB is the number which is above the edge AB, which is 7. So this is 0 plus 7, which is 7. Now this is all we need to calculate corresponding to the labeled vertex A, because corresponding to the labeled vertex A, there is only one adjacent unlabeled vertex that we have, which is namely B. So we have calculated the D dash for B. Now we take a look at the labeled vertex D. Now corresponding to the labeled vertex D, there are 2 adjacent unlabeled vertices that we have, namely F and E. So we make the calculations for F and E. So for F, we calculate the D dash, which is the distance moved in traveling till the vertex F, and we have to again assume that to reach F from vertex D, we will be moving along the edge DF. So this is going to be DD, the distance traveled till D, plus the weight of the edge DF. So this is the distance traveled till the vertex F. Now DD, this is the DD, this is the distance traveled till the vertex D. So this is 5, plus the weight of the edge DF is the number which is over the edge DF, which is 2. So this is equal to 7. So 7 is the D dash for the unlabeled adjacent vertex F. There is another unlabeled vertex, adjacent unlabeled vertex corresponding to the labeled vertex D, which is E. So we make the calculations for E also now. Now we calculate the D dash for E. With the D dash for E is, again we will have to assume that to reach the vertex E, we will be traveling along the edge DE from the vertex D. So this is going to be DD, the distance traveled till D, plus weight of the edge DE. So this is going to be DD, as usual is 5, and the weight of the edge DE is going to be 4. We can see from the graph 4 is associated with the edge DE, it is the weight of the edge DE. So this is going to be 9. So we have calculated D dash for E also. So these are the D dashes corresponding to the adjacent unlabeled vertices F and E corresponding to the labeled vertex D. Now the only labeled vertex which is now left is C, and the adjacent unlabeled vertices corresponding to this labeled vertex C are G. G is the vertex which has not received any label and it is adjacent to C. Then F is the vertex which is adjacent to C and it has not received any label. So G and F are the two adjacent unlabeled vertices corresponding to the labeled vertex C. So for G we make the calculations. Again we calculate the D dash for G. D dash is going to be, again we have to assume that D dash is the distance travelled in moving till G. And when we are moving from the vertex C to G, we will be just think, imagine as if we are moving from C to G along the edge CG. So this is going to be DC, the distance travelled till C, plus the weight of the edge CG. And this is DC is actually this is the distance travelled till the vertex C, which is 6. So this is 6 plus the weight of the edge CG is 3. So this is going to be 9. So this is the D dash for the adjacent unlabeled vertex G. And now the other adjacent unlabeled vertex corresponding to the labeled vertex C is F. So again we make the calculations for F. We calculate the D dash for F. So D dash is going to be DC, the distance travelled till C, plus the weight of the edge CF, because we'll be assuming that we'll be following the edge CF to move from C to F. And DC as usual is 6, and the weight of the edge CF is 5. So 6 plus 5 is 11. So these are the D dashes that we have obtained so far. One is 7, the other is 7, the other is 9, then we have 9, and then we have 11. These are the D dashes that we have obtained in this step. So we find the minimum of all the D dashes that we have obtained in this step, which means that we have to find out the minimum of 7, 7, 9, 9, 11, and the minimum of course occurs, the minimum is 7, and which occurs at two places. So the minimum is occurring at this position, and the minimum 7 is also occurring at this position, which means that the minimum occurs for the adjacent unlabeled vertex B corresponding to the labeled vertex A, and the minimum also occurs for the adjacent unlabeled vertex F corresponding to the labeled vertex D, which means both B and F will receive a label. The label which B will receive will be A7, because A is the labeled vertex corresponding to the unlabeled vertex B, and this 7 is the D dash corresponding to B. So this D dash can be referred to as DB, which is the distance travelled till B. Again the other vertex which will be receiving a label will be F, and the label which F will receive will be again D7, because D is the labeled vertex corresponding to the unlabeled vertex F, and 7 is the D dash for F, and this D dash can also be written as DF, which is the distance travelled till F. So these are the two labels that we'll be now adding in the graph for vertices B and F respectively. So B is now given a label in the graph. The vertex B is now given a label, and the label that B receives is A7, and the label which F receives is D7. So by the end of step 4, the vertices which have now been labeled are vertex A with this as the label, vertex D with this as the label, the vertex B with this as the label, the vertex C with this as the label, and the vertex F with this as the label. So there are 5 vertices which have received labels so far by the end of step 4. Again we proceed with step 5 in a similar manner. Now proceeding on to step 5. Now in the graph we can see there are 5 labeled vertices that we have. The labeled vertices are A, B, C, D and F, and now corresponding to each of the labeled vertices we will be finding the adjacent unlabeled vertices, and then we will be proceeding on to calculate the D dashes for each of the adjacent unlabeled vertices. Now the first thing is that considering the labeled vertex A, now if we take a look at the labeled vertex A, there is no adjacent unlabeled vertex corresponding to the labeled vertex A, because there are 3 vertices which are adjacent to A, namely B, C and D. B is adjacent, C is adjacent, and D is adjacent to A, but none of them is unlabeled. All the 3 are labeled, which means that there is no adjacent unlabeled vertex corresponding to the labeled vertex A. So this vertex will not contribute anything in this step. Now coming to the second labeled vertex, which is B. Now corresponding to B, there is only one vertex, namely G, which is adjacent and unlabeled. So we calculate the d dash for g, which is d dash is the distance traveled in moving till g, and d dash till g will be equal to db, the distance traveled till b plus the weight of the edge bg, because we'll be assuming that from the vertex b will be moving to the vertex g via the edge bg, and db is the distance traveled till b. Now again we can see that the weight that the label that was given to the vertex b was a7. So this means that this 7 stands for db, the distance traveled till b. So db is 7 plus the weight of the edge bg is the number which is written along with the edge bg, which is 4. So 7 plus 4 is 11. So this is the d dash for g. So these are all this is the only calculation that we have for this particular labeled vertex b, because there is only one adjacent unlabeled vertex g corresponding to the labeled vertex b. So now coming to the third labeled vertex, which is C. Now as far as C is concerned, C has just one vertex which is unlabeled and adjacent, and that is G again, and corresponding to this adjacent unlabeled vertex G, we will calculate d dash. So d dash comes out to be dc, the distance traveled till C plus the weight of the edge CG, because again we have to imagine that we are moving along the edge CG from the vertex C to G to reach to the vertex G. So again DC can be obtained by using the label for C. The label that was given to C was A6. So this 6 actually stands for DC, the distance traveled till C. So DC is 6 plus the weight of the edge CG. The weight of the edge CG is 3. So 6 plus 3 is 9. So we have obtained the d dash for G also, which is coming out to be 9 in this case. So again now the next labeled vertex is D. Now corresponding to the labeled vertex D, the adjacent unlabeled vertices corresponding to the labeled vertex D, again there is only one vertex that is adjacent and unlabeled, which corresponds to D, and that is E. So E is the only unlabeled adjacent vertex, and we calculate the D dash accordingly the way we have done in the previous steps for this unlabeled adjacent vertex E, and D dash is DD, which is the distance traveled till D plus the weight of the edge DE. So D dash is DD, the distance traveled till D plus the weight of the edge DE, because again we will be imagining that we are moving from D, the vertex D, capital D, to the vertex capital E along the edge DE. So DD is again obtained by using the label for D. The label for D was A5. So because the label for D was A5, so this is your DD. So this is going to be 5. The value of DD is 5 plus the weight of the edge DE is 4 from the graph. So this is 9. So this is for the labeled vertex D. And now coming to the last labeled vertex, which is F. Now corresponding to this last label vertex, which is F, there are two unlabeled adjacent vertices, namely G and E are there, and now corresponding to G we calculate the D dash. The D dash corresponding to this is going to be DF, the distance traveled till F plus the weight of the edge FG, because again we'll be assuming that we are moving along the edge FG to move from the vertex F to G. So DF, again the label that we gave to F was D7, and this 7 stands for DF, the distance traveled in moving till F. So DF is 7 plus the weight of the edge FG is 4 from the graph. So this comes out to be 11, and then we calculate the D dash for the vertex E. The D dash for the vertex E is again DF, the distance traveled till F plus the weight of the edge this is going to be FE, because again we are assuming that we are traveling along the edge FE to move from the vertex F to the vertex E, and DF again is 7 and the weight of the edge FE is 6. So 7 plus 6 is 13. So So we have obtained all the d dashes in this step, and the d dashes that we have obtained in this step are 11, 9, 9, 11 and 13. So there are 5 d dashes that we have obtained in this step, and now we are going to calculate the minimum of all the d dashes that we have obtained in this step, which is 11, 9, 9, 11 and 13. So we are going to find the minimum, and the minimum of course is 9, which is occurring at 2 positions. The minimum is occurring at 2 positions. One is this and the other is this, which means that the minimum occurs for the unlabeled vertex G, the adjacent unlabeled vertex G corresponding to the labeled vertex C, and the minimum also occurs for the unlabeled vertex E corresponding to the labeled vertex D, which means that G and E are the 2 vertices which are of importance, and G the adjacent unlabeled vertex G will now receive a label, and the label will be C9, because G corresponded to the labeled vertex C, and 9 was the D dash that we had for the labeled vertex G. So this 9 actually stands for the D dash for the labeled vertex G, or this 9 stands for the DG, the distance traveled till G. And again the other vertex which receives the label is E. So the label which is received by E is D comma 9 again, because D is the labeled vertex corresponding to the unlabeled vertex E, and 9 is the D dash for E, or we can say that this D dash is DE, the distance traveled till E. So there are 2 vertices which are receiving a label, G and E. So the label which is received by G is C9. We put it in the graph, and again we add the label of E in the graph, which is D9. So all the vertices have been labeled except for the vertex H, which has not been labeled so far. So this means that the procedure has still not ended. We still have to move forward to give a label to H, which has still not received a label so far. So moving on to step 6, we will again collect all the labeled vertices that are present in the graph so far. So the labeled vertices are A, B, C, D, E and F and G. These are all the labeled vertices, and corresponding to each of these labeled vertices we'll find the adjacent unlabeled vertices, and then we'll proceed on to calculate the D dashes in the same way, the way we did in the previous steps. Now as far as A is concerned, we can see that A doesn't have any adjacent unlabeled vertex associated with it, so A will not contribute anything in this step. Again the same thing goes for B. B will also not contribute anything in this step, because B has no associated adjacent unlabeled vertices along with it in the graph. Again C also doesn't have any associated adjacent unlabeled vertex. And then looking on to D, again D also doesn't contribute anything in this step, because D has no adjacent unlabeled vertex. All the vertices which are adjacent to A, B, C, D, they are all labeled. And then for F again the same thing we have. There is no adjacent unlabeled vertex that we have corresponding to F. So as far as these 5 vertices are concerned, A, B, C, D, F, they do not contribute anything to this step, because they do not have any adjacent unlabeled vertices. Now coming to the labeled vertex E. Now corresponding to E, there is one adjacent unlabeled vertex that we have, which is namely H, and we find the D dash corresponding to this adjacent unlabeled vertex H. So D dash corresponding to H is going to be DE, the distance traveled till E, plus the weight of the edge EH. Again we'll be assuming that we are moving along the edge EH to move from the vertex E to the vertex H. So the total distance traveled in moving till the vertex H will be the distance traveled in moving till E plus the weight of the edge EH. And now again the label that was given to E was from the graph we can see the label is D9. So this 9 actually stands for DE, the distance traveled till E. So DE is 9 plus the weight of the edge EH from the graph is 5. So 9 plus 5 is 14. So 14 is the D dash for the adjacent unlabeled vertex H corresponding to the labeled vertex E. So these are the calculations for the labeled vertex E, and now coming to the last labeled vertex which is G. Now again we can see that corresponding to this labeled vertex G, there is one adjacent unlabeled vertex which is again H. So we calculate the d dash for this H, and the d dash is the distance travelled till H, which is the distance travelled till G plus the weight of the edge G H, because again we'll be assuming that to move till H from the vertex G, we'll be moving along the edge GH. So again dg can be obtained from the label of G. The label that has been given to G was C9, and this 9 is actually dg, the distance travelled till G. So dg is going to be 9 plus the weight of the edge GH. The weight of the edge GH from the graph is 4. So 9 plus 4 is 13. So there are two d dashes that we have obtained in this step, which is 14 and which is 13. And now again we do the same thing which we have been doing in all other steps. We find the minimum of these d dashes, which is 14 and 13, and the minimum of course is 13, which occurs for the adjacent unlabeled vertex H corresponding to the labeled vertex G, which means that the H is the vertex of importance now, and H will now be labeled, and the label that we will give to H is G, because G is the corresponding labeled vertex, and G comma 13, because 13 is the d dash for H, or this 13 can now be just denoted by dh. This is the distance travelled to move till H. So the label which we give to H is G13. So all the vertices have now been labeled, including the starting vertex which is A and the end vertex which is H. So now we are in the position to find out the shortest route between the vertex A and the vertex H. And now to find the shortest route between the vertex A and vertex H, what we do is we just write the labels in a backward manner. Now H was the last vertex in the route, so the corresponding to H, the label which H has received is G13. This is the label, so we write the labels here. And now here you have G, so now corresponding to G we write the label. Now corresponding to G, the vertex G, the label which G has received from the graph, we can see it is C9. So again now C is the vertex which we have to write. Now C, the vertex C has a label from the graph, which the label which C has is A6, and A is the, of course, the first starting vertex whose label we have already given initially. This is the label which we gave to start the method, which is -0. So now this starting from the last step to the first step, this is the shortest route, which means that the shortest route is from A you have to go to C, and from C you have to go to G, and from G you have to go to H. So this is the shortest route. This is the route that you have to follow, and the shortest distance along this route is the distance which is that we have traveled to move till H, which is 13, that is dh. So this is coming from the label of H. So the shortest distance is 13, and the shortest route is ACGH. So this is how the shortest route is calculated. So although the algorithm is complete in itself by now, but there are a few things that have to be noted before we end this video. Are the following things which one can note. The first thing is that if there is some adjacent unlabeled vertex, let's say Z, which is adjacent to, let's say, two labeled vertices X and Y, and suppose the minimum occurs at this vertex Z, which the minimum D dash occurs at this vertex Z, which means that Z will now receive a label, because at whichever vertex the minimum occurs, that vertex has to be labeled. So Z will receive a label, but then Z is now adjacent to two labeled vertices X and Y. So in such a case, whenever such a situation arises in some step, then Z can either be labeled as X D dash, or we can give label Y D dash to Z. So these are the two possibilities that we have. We can choose any of the two possibilities. So this is one thing that has to be noted upon. And now the second thing which needs to be noted upon is that if we pick up any vertex, let's say I pick up the vertex G, in the graph, and the label that G has is C9. So I'm picking the vertex G, and the label which G has is C9. So this 9 actually signifies the distance, the shortest distance between the starting vertex A and the vertex G. So this is one thing that has to be seen. And again C, this C helps me to get the shortest route. Of course, the shortest distance between A and G is 9, and to get the shortest route we can make use of C, because if we want the shortest route between A and G, so the label which G has is C9. Again we write the label for C. The label for C from the graph is A6. Now moving in a, and again the label which A has is -0, which we gave in the beginning, although we don't need this label. Now again moving in a backward manner, the shortest route from A to G is from A you have to go to C, and from C you have to go to G. So I'm moving in this manner from A to C, and then from C to G. So this is the shortest route, and the distance traveled along this route is this number 9. So this is for the vertex G. The same thing can be done for any other vertex. Let's say we pick up the vertex E with label D9, then again the shortest distance between the starting vertex A and the vertex E will be 9, and also we can find out the shortest route between A and E by back tracing the labels. So for every vertex in this graph, we can find out the shortest distance between that vertex and the starting vertex A. So this is the second point that has to be noted. And the third and the last point which can be noted over here is, although in this particular example we have taken the weights to be distances, and the distances between two cities, and these are the distances in kilometers, but instead of the weights being taken as distances, these weights could have been time taken along the routes. Let's say if 7 is written, then 7 might represent the time which is taken to move from city A to city B, and this 4 might represent the time taken in hours to move from city B to city G. In that case, we have to again proceed in the same way, but the shortest route that will be obtained in the end from A to H, that shortest route will be the route along which the time taken is the smallest, or the route which takes the least possible time in moving from A to H. So these weights can even represent the cost of from ticket via some public transport in moving from one city to another. In that case, if you get the shortest route from A to H, then that shortest route from A to H will actually represent the cheapest route. Depending upon the context, whether the weights are distances that are given, or the weights are the amount of money involved in traveling from one city to another that is given, or the weights are the time which is spent in traveling from one city to another that is given. Accordingly, the route will be either the shortest route if the weights are distances. In terms of distances, it's the shortest route. If the weights are if weights represent the time taken, then the route will be the shortest route will be that route along which the time taken is the least. And if the weights are the amount spent in moving from one city to another, then the shortest route will actually be the cheapest route, which is economically the cheapest of all the routes in moving from the city A to city H. So that was all about the shortest path algorithm and the problem of finding the shortest route between two cities.